Hello. Today we're going to talk a little bit about the properties of braid groups. In particular, we're going to focus on braid groups that are B3 or greater. We know B2 is isomorphic to the integers, meaning it has the same properties as the integers under addition. And we know that B sub 1 is isomorphic to the trivial group. With one strand, you can't really say a lot about how it twists around other strands because there's no other strands to twist around. So assuming we're working in braid group Bn, then it turns out if we define a element omega, which is going to be sigma 1, sigma 2, all the way up to sigma n minus 1, all raised to the power of n, then it turns out that omega times sigma I is equal to sigma I times omega for all I. In particular, we mean 1 less than or equal to I less than or equal to n minus 1. I's that make sense in the context of the given Bn. So what this tells us is omega is going to be inside of the center of Bn. But we can do a little bit better than that. Without proof, it turns out that the center of Bn, all the elements that are going to commute with any arbitrary braid in Bn, this is equal to the group generated by omega itself. The next property is about some subgroups of braid groups. There's one I want to focus on first. In particular, if we have m less than or equal to n, it turns out that b sub m is a subgroup of b sub n. The way we can show this is we can define a mapping, psi, which is going to map from the elements of bm to elements of bn, given by psi of sigma I equals sigma I. It turns out that psi is 1-to-1. Therefore, because it's 1-to-1 and it's also a homomorphism, then Bm is going to be a subgroup of Bn. Geometrically, this can be shown by imagining you have maybe n strands over here, or rather m strands. But if we instead had the full n strands, we can have all these over here, all of the m strands. And then you have the remaining n minus m strands over here. So if we imagine all the braids that leave these fixed and unchanged, but that twist these strands over here, then we can see how we get a subgroup. Because any operations we do twisting only the left set of strands, ignoring the right set of strands, while combining other types of braids where the right set of strands are ignored, will have closure, and we'll also have inverses and identities and all the stuff we'd associate with groups and subgroups. For every non-trivial braid group, the order of the braid group is going to be infinite, but we can do a little bit better. The order of each generator, sigma I, is going to be infinite. In fact, for every non-identity element, for all beta in Bn such that beta is not the identity, it turns out the order of beta is always going to be infinite. Why is this the case? We know that no braid is going to be its own inverse. If we were to have a certain twist, undoing that twist would require us to go through the reverse twists, the exact same order. That cannot occur. I'll leave the details of the proof as they're shown in the book. Now, that being said, that doesn't mean that we can't study a fair bit about these types of twists. One thing we might notice is if we have a braid that has some kind of twisting going on maybe, and then it results in the following bottom. This is in B6, but it can be in any braid group. But if we look at these strands that start 1, 2, 3, 4, 5, 6, we can see where they end up. 1, 2, 3, 4, 5, 6. And this will give us the permutation of the strings between the top and the bottom. We usually represent these in tables like so. 1, 2, 3, 4, 5, 6, and then maybe if the first string here moves to the position of the third string, we put a 3 here. Second string stays fixed, we put a 2. Third string goes to the position of the sixth, fourth goes to 1, 4 goes to 5, 5 goes to 6. So no idea what's going on with twisting in the middle, but what we do know is when it's all said and done, we might have some kind of permutation of the starting and ending points like so. There's a special class of braids, and these are called the pure braids. And the rule for a pure braid is it's going to be any braid where the permutation is the identity permutation. Each string starts and ends in the same slot. That doesn't mean that no twisting occurs, but what it does mean is that when all the twisting is done, each string starts and ends at the same spot. We're going to denote the set of all pure braids, P sub n. What's special about the pure braids is it turns out the set of all pure braids, P sub n, is a subgroup of B sub n. This can be shown by noting that for all beta 1 and beta 2 inside the set of pure braids, beta 1 inverse is also a pure braid. We know that if we go backwards from our permutation, we still have the identity. Hence, every pure braid's inverse is also a pure braid. We also know that beta 1, beta 2 is going to be a pure braid as well, because if we imagine feeding through the permutation kind of table here, 1 goes to 1 goes to 1, 2 goes to 2 goes to 2, and so on. But we can make a stronger claim. It turns out that the set of all pure braids forms a normal subgroup of Bn. And furthermore, if we take the quotient group Bn quotiented by Pn, this is isomorphic to the permutation group on n elements, Sn. So if we know some things about the set of pure braids, we can learn a little bit more about the structure of the braid group Bn. That's all for this video. Next video we'll talk a little bit about invariance, and then we'll get into S-isotopy afterwards.